All right, let's get started. Welcome, everybody. Welcome to the start of the spring 2021 semester of the New York Group Series Seminar. So we're still meeting online, so we'll see what happens later. So I hope that everybody is doing well. So welcome back. And I'm pleased to introduce our first speaker this semester, Vladimir Shpilrain from the City College. And he's going to tell us something about what, if anything, can be done in sublinear time.
Thank you. Yes, indeed. So Yuri Gurevich gave a talk with a similar title in September last year. The only difference was that he was talking about linear time. So he gave us a survey of some algorithms that terminate in linear time with respect to the length of an input. So I'm gonna try to give a survey of something that can be done in sublinear time. In particular, an algorithm that terminates in sublinear time should not read the whole input, which may sound weird, right? But there is a well-known example, right? Here's a divisibility of a decimal integer by 2, 5, or 10 can be decided by reading just the last digit. You don't have to read the whole input, just read the last digit. And in fact, this is a rare instance where both yes and no answers can be given in sublinear time. So in this case, actually in constant time. Typically, when we talk about algorithms that terminate in sublinear time, these algorithms typically are like tests, fast checks, and they only give like a negative answer typically in sublinear time. Also, another comment on this simple example is that you may feel that there is some kind of cheating involved here because an input here is given you in a decimal form, which is a kind of a normal form of an integer, right? So with a different normal form, it would be different. Like if it was a binary form, then you would be able to decide divisibility by 2 by looking at the last digit, but not divisibility by 5, right? So this kind of depends on the normal form that you have for your input. And if you didn't have an integer in any normal form, so basically an integer n is just a collection of n sticks, right? So then what can you do? To represent such an integer in whatever form, like decimal form, it takes linear time. There's no way around that. But since in real life, I mean, whenever we have integer as an input, it's either in decimal or in binary form in like 99% of cases. So we're okay with that. We're okay with this kind of result, saying that there's a sublinear time algorithm that decides the divisibility of a decimal integer by 2, 5, or 10. Not by 3, though, right? So this kind of algorithm has a limited application. Now, so these typical sublinear time algorithms, like I said, fast checks, they are Las Vegas types algorithms. Well, at least we are primarily interested in Las Vegas type algorithms as opposed to Monte Carlo type algorithms. Why? So what's the difference? A Las Vegas algorithm never gives a wrong answer. It may not give an answer at all. It may say, I don't know, but if it does give an answer, the answer is correct. In contrast, a Monte Carlo algorithm may give an incorrect answer, typically with a small probability. Now, why is a Las Vegas algorithm better for our purposes. That's because what we can do if we have a fast Las Vegas algorithm for a fast check of certain property, we can run this algorithm in parallel with an honest algorithm. By an honest algorithm, I mean an algorithm that always terminates in finite time and always gives you a correct answer. So if you think about the word problem for groups, for example, right? So some groups, they do have a solvable word problem, but sometimes with the algorithm with high complexity, sometimes exponential complexity. But there might be a fast check, like check in the abelianization of your group that may give you a fast no answer, meaning that the word, the element is not the identity in the group. And when you run two algorithms in parallel, then the average case complexity of this composite algorithm may be lower than the complexity of the honest algorithm. And this was explored, and many examples of this sort were given in these two papers with Ilya Alexey and Paul Shub. Their results that describe specific situations where the average case complexity is actually lower than complexity of the hard working algorithm. Yes.
Can I ask a question? How does it inform about the failure? I mean, how does it inform? What does it say? What's the output?
It says, I don't know. So in reference to the abelianization check, so you check whether your element is the identity in the abelianization. If it is not, then it is not the identity in the whole group. But if it is, then your test is inconclusive. And the algorithm says, I don't know, the test is inconclusive. Okay.
Thank you.
All right, so there are also examples in graph theory, even though I'm not gonna talk about those, but there was a lot of activity generated by this seminal paper, where in particular it was pointed out that the problem of K colorability of graphs, which is NP complete to determine precisely for any K greater than 2, but it may be efficiently testable, well, again, if you are lucky, right? For example, if you randomly sample a graph with, let's say, K plus 1 vertices, and this graph turns out to be complete, then this graph is not K colorable, and therefore the whole graph is not K colorable. So this is philosophically similar to the example on abelianization check that I mentioned, right? So if you are lucky, your small graph on K plus 1 vertices will be complete, and then you are done. The graph is not K colorable, but you cannot give a positive answer with this fast check, only a negative one. Well, of course, I mean, you see that it's a paper that is almost 100 pages long, and it was written by very serious computer scientists. So there is much more to that paper than just this simple observation. But yeah, I'm mentioning this just to say that in graph theory, there was a lot of activity at the turn of the century on sublinear time testing of various properties of graphs. But in my talk, I will focus on groups and semigroups. Okay, so well, our first in this talk first example of a non-trivial and perhaps somewhat surprising result on sublinear time algorithms will be a theorem of Sonoff. That's a very old theorem. It says that the group generated by two matrices that I denote here by A of 2 and B of 2 consists of all matrices of this form with determinant 1. So you see that deciding whether a matrix is of this form amounts to checking divisibility by 2 or 4, divisibility of an integer. We're talking about matrices over integers. And divisibility by 2 or 4 of an integer given in a decimal or a binary form can be done in constant time. Right? In case of divisibility by 2, you look at the last digit. For divisibility by 4, you look at the last 2 digits. So this is as good as it gets, right? It's a constant time algorithm, and it's an if and only if, so it gives you both yes and no answers in constant time. Of course, one might want to generalize this to other k, right, to k greater than 2. So the natural question was, does this theorem of Sonoff generalize to k greater than 2? But the answer is no. So in this paper, we showed that the subgroup of the special linear group over Z generated by A of k and B of k for k greater than 2 has finite index in the group of all matrices of this form. But still, it does have this form, right? So for a fast check, it is still good. You can check if your matrix has this form, and if not, then it does not belong to the subgroup in question. And checking whether a matrix is of this form, again, amounts to checking divisibility of integers, this time by some k greater than 2. And again, it just reduces to the problem of divisibility of a decimal integer by a certain k. For some k, there is a sublinear time algorithm. For some k, like 3, for example, there isn't. So that's the situation here, right? It's interesting that it depends actually on the value of k, right? So for some k it works, for some k it doesn't.
So Vladimir, you're assuming here that the elements of SL to Z are given to you with entries in binary or in decimal form, right?
Yes, either in binary or in decimal. Like I said in the beginning, that's how we usually interpret integers. Okay, now after our paper was published, there was another paper that may give a false impression that there is still an honest sublinear time algorithm for deciding subgroup membership in that group generated by A of k and B of k. So namely, there was this theorem. So a matrix of this form, well, it should be of this form if we want our matrix to belong to that subgroup. It does belong to that subgroup if and only if and there is this condition. So there's a ratio of one of the entries to another, and one of these ratios should have a continuous fraction representation with all partial quotients divisible by k. And partial quotients representation can be obtained in time, which is sublinear in the maximum of the entries of the matrix. So yeah, it may look like this is a sublinear time algorithm, right? Because it's its logarithm of the maximum of the entries of a matrix. But the thing is that the size of the entries of the matrix does not reflect the complexity of the input. So when you input an integer in a decimal form, for example, the complexity of this input is not the value of this integer itself. It's logarithm of this value. It's logarithm of the integer, right? So the actual length of this decimal or binary representation of an integer, it's logarithm of the value of the integer. So what this theorem says is that the complexity of this algorithm is big O of logarithm of the maximum value of the entries of the matrix, but that means it is linear in the size of the input. So this is not a sublinear time algorithm, it is a linear time, which is still remarkable, right? So for a problem like that, to have a linear time algorithm is still very good, but it is not sublinear time. Okay, so let's move on to more combinatorial group theory. Let's talk about detecting primitive elements of a free group. So an element of a free group is primitive if it is part of a free basis, or equivalently if it can be taken to X1, to one of the standard free generators, by an automorphism of the free group. Then let's define the Whitehead graph of an element of a free group. It has two R vertices corresponding to generators, R generators, and their inverses. So the number of vertices is fixed. It does not depend on the size of the input word W, right? So the size of the graph is, well, the number of vertices at least is fixed, and it is 2R. Now, the edges. So for each occurrence of a subword, xi, xj, in the word W, there is an edge in this graph that connects the vertex that corresponds to xi to the vertex that corresponds to xj inverse, and so on. And there is one more edge, the external edge, that connects the vertex corresponding to the last letter to the vertex corresponding to the inverse of the first letter. That's the Whitehead graph. And Whitehead himself observed that the Whitehead graph of any cyclically reduced primitive element W of length at least 3 has either an isolated edge or a cut vertex. So it's important that the input should be cyclically reduced, right? Because, for example, take X1 and conjugate it with any element. It's going to be a primitive element still, right? But the Whitehead graph of this could be anything at all. So it's important that the element is cyclically reduced. And here we're again have to talk about the input, the form of the input, right? So when we think about elements of a free group, we think of words in generators and their inverses, words that are freely reduced. So words that do not have subwords of the form xi, xi inverse, or xi inverse xi. Because if a word is not freely reduced, then for most purposes, including this, including detecting primitivity, you first have to freely reduce it. And this will take linear time. This is unavoidable. So we will have to, in what follows, we will have to assume that the word given to us is freely reduced. With cyclically reduced, it's not that important. I mean, to cyclically reduce a word is different, right? Well, at least to detect if a word is cyclically reduced or not is easy, right? You just look at the first letter and the last letter. So it's constant time. But to detect whether the word is freely reduced or not, you will have to read the whole word.
Sorry, why do you mean it's constant time? To access the first letter and the last letter, don't you need to read the entire word?
No.
No?
I just need to read the first letter and the last letter.
Okay.
Well, I mean, it depends on how this input is given to me, right?
You mean like to read, Vladimir, to receive the last letter, you have to read the whole word? Or-
Well,
Not necessarily. Well, again, it depends on how this word is given to me, right?
Yeah.
So, well, yeah, strictly speaking, yeah, I have an oracle that responds to an inquiry about any particular letter, right? So then I can decide a cyclic reducibility, or rather cyclic irreducibility, well, both actually, in constant time. But this won't work with just free reducibility. Okay, anyway, so now we want to decide whether a given word represents a primitive element of a free group or not. So we call a word, again, a freely reduced word, primitivity blocking if it cannot be a subword of any cyclically reduced primitive element of a free group. For example, if the Whitehead graph of W has a Hamilton circuit, then W is primitivity blocking, because in that case, the Whitehead graph of W does not have a cut vertex or an isolated edge, and therefore the whole Whitehead graph does not have a cut vertex. And then a fast testing algorithm to test primitivity of a cyclically reduced word. Again, I emphasize that it has to be reduced. Cyclically reduced, not so important, but it has to be freely reduced. So it would work as follows. You build the Whitehead graph of your input element U, one edge at a time, going left to right, and check if the resulting graph is Hamiltonian. Well, you may say that the problem of checking if a graph is Hamiltonian is NP hard, but here the size, the number of vertices of the graph is fixed, and it is a constant with respect to the length of the input. So it does not influence complexity of our algorithm, this checking. At the same time, the usual Whitehead algorithm with Whitehead reductions and stuff can be run in parallel. And this usual or honest Whitehead algorithm, I think it runs in time n log n, where n is the length of the word U. So you run these two algorithms in parallel. And here's the problem. What is the average case complexity of this composite algorithm? Is it sublinear with respect to the length of the input? I would expect that the answer is yes, because like I said, the complexity of the honest Whitehead algorithm is already quite low. It's almost linear. And most of the time, the fast testing algorithm T will give you an answer much sooner. So the expected running time of this algorithm, in the usual sense of probability theory, the expected running time, I expect it to be sublinear. And this would be a very interesting result. So that would be a very natural problem that would have an average case solution sublinear. Okay, so with this in hand, one may ask, what about other blocking words is there something analogous for other automorphic orbits, right? So take an arbitrary element U of a free group, consider the orbit under the action of automorphisms of the free group, and call an element W orbit U blocking if it cannot be a subword of any cyclically reduced element in the orbit. Again, we need cyclically reduced condition for the same reason. Okay, so in particular, is there an algorithm that on an input U from a free group would output at least one particular orbit U blocking word? Well, I mean, orbit U blocking words should exist for any U by counting sort of arguments, but to find a particular orbit U blocking word for a given U, I don't know how to do that, except for this very special case where U is the commutator of two generators, x1, x2, and moreover, if the rank of the free group in question is 2. Then, by the classical result of Nielsen, any cyclically reduced word in the orbit of this U is either the commutator of x1, x2 itself, or its inverse. So this is a spectacular sort of situation, right? Like most words will be orbit U blocking in this case. So there's only like a couple of words that are not orbit U blocking. This never happens in other situations. Even for primitivity blocking, there are infinitely many words that are not primitivity blocking, like powers of any power of x1 is not primitivity blocking. And here is just like a couple of words that are not primitivity blocking. All others are orbit U blocking. But rank 2 case is always special. Well, not always. We know that the first order theory of F2 is the same as first order theory of any FR, but still F2 is special in most cases. Okay, so now we switch gears and let's discuss the word problem. So why do I call this slide the word problem for semigroups rather than groups? For the word problem for groups, there is nothing really that we can do in sublinear time, not even like a partial answer. Because, well, if you look at, let's say, at the half of the input, so you have this input word U, you look at the half of U, and whatever this half of U is, it usually cannot tell you that this word is not equal to 1 in the given group G. Well, for the half, I don't know. I mean, it depends on the length of relators. Yeah, and I'm assuming that the group G is given by generators and defining relators, right? So depending, of course, on the length of these defining relators, it might not be necessarily a half, but let's say that n is the maximum length of your defining relators, then by examining the part of U of length U over n, you cannot tell anything about this word, this whole word being or being not equal to 1 in the group, because the remaining part of the word can do either way, right? Can either make this word equal to the identity or not. So sublinear time for the word problem for groups just don't exist. For semigroups, it's a different matter. So that's how the word problem for semigroup sounds. Given two words, and generators find out whether or not they are equal, right? And the meta problem is, are there natural examples of semigroups given by generators and relators where the word problem admits a sublinear time solution, well, at least for most inputs, or at least for some inputs, right? At least something. And if such a sublinear time algorithm exists, it can only give negative answer. Negative answers. That means that G is not equal to H, because to prove that they are equal, you will need to read the whole inputs. And again, I remind you of our paper on generic case complexity, where generically linear time solution of the word problem was offered for large classes of groups. But these are only negative answers. Okay, so the class of examples that we're going to look at right now, they are positive monoids associated with groups. That means they are monoids generated by group generators, but not their inverses. And for some particular groups that are very popular in group theory in the last decade, like Thompson's group or braid groups, these monoids, in fact, have been extensively studied. So let's see what we can do with the word problem in those positive monoids. So let's start with Thompson's group F. Here is a semi-group presentation of this group, right? So defining relators here are positive words. So it's a semi-group presentation. And we can talk about the positive monoid associated with this presentation. We're going to call it F plus. And unfortunately, the result here is negative. So this is a proposition for any two positive words of length m and n respectively in these generators, in the standard generators. There are other positive words of length n and m respectively, such that this quality holds. So it's sort of an or condition, right? In group theory, in semi-group theory language. And it's an or condition in a very strong form, right? Not only does it tell you that these words Z1 and Z2 exist, it gives you like precise lengths of these words. And what this proposition implies is that it is impossible to tell that two positive words, well, let's say of the same length L, but the same thing if they don't have the same length. If they are equal in Thompson's, so it should be monoid, positive monoid F plus, by inspecting their initial segments of length less than L or 2. I'm going to prove this proposition just to prove something, right? Because the proof is quite nice and simple and elegant. And the proof is actually due to Victor Guba, who is a well-known expert on Thompson's group. We're going to construct the Van Kampen diagram on a square lattice. We're going to mark the word W1, so one of those two words, horizontally on this square lattice, and the other word W2 vertically by letters. So with W1, the letters go as usual, left to right. With W2, so letters rather than left to right will go bottom to top. Okay, so and now there are a lot of edges inside this big rectangle, M by N rectangle. There are a lot of other edges in the square lattice that have to be marked by letters XI. How do we do that? We do that by, of course, using the defined relators. So that's how we do that, right? But let me perhaps give an example, a particular example where W1 is X1, X2, and W2 is X3, X5, right? So there are two words of length 2. So we mark the word W1 on the horizontal line here in red, X1, X2, the word W on the vertical line. So it was supposed to be blue, but it is almost black. So it's bottom to top, X3, X5. Now, how do we mark edges inside this rectangle, which is in this case a square, a 2 by 2 square? So look at this X3, X1, right? So this is the case where X1 is on the lower edge and X3 is on the left edge, and 1 is less than 3. Then the upper edge is marked by Xi, right? So by the smaller of these two. So this cell corresponds to the relation X3. Sorry, we did not complete the cell. We have also to mark this right edge of this little square by X4, right? Because this is the case where we have the left edge marked by X3 and the upper edge marked by X1. So in this case, the right edge is marked by X3 plus 1 by X4. So now this little cell, this little square, corresponds to the relator X3, X1 equals X1, X4. And we do the same thing with every little square. And now every edge is marked. And on the boundary of the big square, we can now read this equality. So X1, X2, X5, X7 in red is equal to X3, X5, X1, X2 in blue. So that's the OR condition in this case. All right, so anyway, the bottom line is there is no sublinear time algorithm because of this proposition. So examining just let's say half of the words, of the given words, will not allow you to make any conclusions. Okay, so that's a negative result. Now let's see if there is something positive that we can say. So braid groups. Braid groups are very popular as well, right? So that's a standard presentation of a braid group Bn with standard generators. And you see that defining relators here are positive words. So again, we can talk about a positive monoid associated with this presentation. And it turns out that actually, at least for some pairs of positive words in this positive monoid, there is a sublinear time test for inequality. And it follows from from a paper, from this paper by Autor and Dehrenoi. I mean, there is no particular theorem or a proposition in this paper that would imply this proposition on this slide, but it can be recovered from one of their proofs. So the proposition that we're talking about here is this, rather interesting actually. So we have two positive braid words, W1 and W2 like this, and you see that actually W1, it only has odd numbered generators sigma, which means you can write those in any order, because odd numbered generators, braid generators commute with each other, right? Sigma 1 commutes with sigma 3 and with any other odd numbered sigma. Similarly with W2, these are even numbered sigmas, and also they commute with each other. So you can write this word, these generators in any order. Now, suppose there is this kind of ORA condition satisfied. So suppose that W1U is equal to W2V for some positive U and V. But then the lengths of these U and V should be equal to 2m squared, right? So the length of W is m, and the length of W2 is m. But to satisfy the ORA condition, we need U and V to be of a length quadratic in m, right? And what this implies is that if one has two positive braid words of length L, where one of them starts with this funny word W, and the other one starts with the word W2, and K is greater than square root of L, then these braid words are not equal in the positive braid monoid, right? Because to make them equal, you will need to augment them with something that is quadratic in K. But if K is greater than square root of L, this will put you above the length L. So this is an example where a sublinear time algorithm can give you a negative answer. Well, I mean, of course, this is a very special example, very carefully constructed. So the question is whether whether the set of positive braid words with this sublinear property is generic or not, right? So one can ask the following question: is there a generic subset of a positive braid monoid and a positive epsilon, such that for any two braid words representing elements of this positive monoid, the minimum length of words that implement or a condition is greater than k to the power 1 plus epsilon? So in that case, you will have a generically sublinear time algorithm of detecting inequality of words in the positive braid monoid. But that, of course, is a difficult question. Unlike like other questions that I asked in this talk already, this is probably a very difficult question. Okay. Then what? Another popular class of groups, especially lately, is class of nilpotent groups. And there are also positive monoids associated with nilpotent groups, even though most of the time they are not finitely presentable as monoids, right? Even though all nilpotent groups, all finitely generated nilpotent groups are finitely presentable, this is not true with positive monoids associated with these groups, with nilpotent groups. For some small classes of nilpotency, like 1 or 2, this is the case, but not for larger nilpotency classes. But anyway, one can consider infinitely presented but finitely generated positive monoids corresponding to nilpotent groups. And unfortunately, there is no sublinear time algorithm for the word problem in those. So here, just like in Thompson's group, we have a negative result. And I'm not going to give you details on that. I will refer to my paper where this is proved. Okay. And now the point that I have already made before in my talk, but I want to make it again, is that, yeah, I mean, this talk may create an impression that these sublinear time algorithms are rather esoteric, right? So there must be some kind of very special situation where you can even think about sublinear time algorithms, even if you just want to have a negative answer to your question, let alone if you want an honest algorithm that would work in sublinear time. But nevertheless, these fast checks, like in group theory, I refer again to our papers with Ilya, Alexei, and Paul Shuk. Fast checks are useful actually in addressing various problems, not just the word problem, also the conjugacy problem, some other problems in group theory, because when you have a fast check algorithm to run in parallel with an honest algorithm, you can often bring the complexity of this honest algorithm down, right? So these fast checks, they are average complexity boosters, right? And average case complexity is something that was not sufficiently explored in group theory. You know, of course, that originally complexity of algorithms in group theory was all about the worst case complexity. Then this classical paper with Ilya, Alexei, and Paul came out, so that's generic case complexity. But the average case complexity was not really explored in groups where the word problem is solvable, especially, right? So we may ask, for example, what is the best average case complexity of the word problem in a free nilpotent groups? So I'm not asking about all nilpotent groups that might be like too complicated, too complex of a problem, but at least in free nilpotent groups, those are very well understood. So can we use this complexity booster, the fast check, the abelianization check, to bring down the complexity of an honest algorithm in a free nilpotent group? In a free nilpotent group of class C, the standard algorithm for solving the word problem is polynomial, and the polynomial has degree C, where C is the nilpotency class.
But so, Vladimir, it's also, sorry to interrupt, it's also known that it log space, but also TC0, it's very low complexity in terms of circuit complexity.
Right, okay. Yeah, well,
it's a different question that whether it's sublinear time or not. That's I kind of.
Yeah, I don't believe this fast check can bring it to sublinear time, because even the abelianization check is already not sublinear. But to lower the degree of the polynomial, I think it's quite possible. So in this paper on average case complexity, computation that we did in section 3 of this paper, they are relevant to the case where the given group G has an algorithm for solving the word problem, and this algorithm works in sub-exponential time. And also the group G has a factor group where the word problem is solvable in a complexity class C, whatever it is. Could be linear time, quadratic time, sublinear time, whatever. And then this like combined algorithm where two algorithms are run in parallel, one algorithm for the factor group, the other algorithm for the whole group, when they run in parallel, the complexity of this combined algorithm is in class C. So it is lower than the complexity of the algorithm for the whole group G. But there is one subtlety. The quotient group that we're talking about has to be non-amenable for these computations to go through and to sort of produce the answer, the desired answer. With nilpotent groups, this is not the case, and with any groups, if we talk about abelianization, abelian group is amenable, right? So this kind of argument doesn't work. But nevertheless, I mean, in smooth groups like free nilpotent groups, still by straightforward computation, in the spirit of like standard probability theory, I believe the expected runtime of an algorithm, of this combined algorithm, can be computed, and I mean, I'm almost sure that the average case complexity should be lower than the worst case complexity of the honest standard algorithm. So these fast checks, they're really useful in terms of like bringing down the average case complexity. All right, so I know you wish this talk would never end, but all good things come to an end. And the last thing, that's what I am always trying to tell to speakers, right? So you should be able to answer this question. Well, not you, somebody else should be able to answer this question at the end of your talk. So if somebody is not present at your talk, like for example, Sasha Ushakov is not present right now, and suppose he will ask Alexei, what was Vladimir's talk about? Was it the usual crap? And so then Alexei should be able to say something in just a couple of like sentences.
I will say it, not usual crap.
I know, right? So 2 points. So I think this I already mentioned. So the worst case and generic case complexity have been already well studied, but this is not the case with the average case complexity. So it may be time to seriously address the average case complexity of algorithms and group theory. And the second point is, again, that was a recurrent theme in this talk, that fast checks, but only those that are Las Vegas type algorithms, not Monte Carlo type algorithms. Fast checks that are Las Vegas type algorithms can be used and should be used to boost performance of well-established honest algorithms and reduce their average case complexity. So this is what Vladimir's talk was about. And that's it. Thank you.
All right. Thank you very much, Vladimir. Let's thank Vladimir. Okay, now if there are any questions to the speaker, you're welcome to ask them.
Excuse me, can you tell again what's the difference between generic case and average case complexity?
Generic case complexity is a complexity on a random input, whereas average case complexity is the expected running time in the usual sense of probability theory. right? Like the expected value. So,
So-
you compute the probability of a certain element coming from a certain set times the measure of this set.
But the randomness is in generic case as well, right? The measure.
Yes, yes. In both cases, you need to somehow define measure of subsets. Yes, this is not trivial for infinite groups, but I mean, I can refer you to our generic case paper. This is usually done by means of asymptotic density. So you consider balls in the Cayley graph of your group, balls of increasing radius, and you see what happens when the radius of the balls goes to infinity. If there is a limit, then that's a good interpretation of a measure on an infinite set.
So that would be an on average, right, approach.
With any approach, with on average or generic case approach, you still need a measure on a subset. So if you have a subset S, which is typically infinite, you intersect this subset S with a ball of radius n in the Cayley graph of your group. Compute the number of elements in this intersection. It will depend on n, on the radius of the ball. And then, if there is a limit when n goes to infinity, of a certain ratio, then that's the measure.
But I mean, conceptually, the main difference is in generic case complexity, you do not average the running time. So on some negligible set of inputs, the complexity can be very high or even undecidable, and the generic case complexity doesn't care. But that might kill the average case complexity still.
Yes.
Okay, thank you.
Yeah, I mean, the standard example to which people usually refer in papers on generic case complexity is the Klee-Minty algorithm for linear programming. The worst case complexity of this algorithm is exponential, but instances where you have to deal with this worst case scenario, these instances are very rare. So in real life, you deal with instances that are solvable in linear time. So you don't care what happens on those small sets of inputs where your algorithm stutters. That's generic case.
Thank you.
All right. And other questions? All right, let's thank Vladimir again. Thank you. So I'll stop the recording now in a moment.